Alright, hello and welcome to Verifying Trig Identities. This is your first lesson for NTI for Advanced Precal, and we are picking up where we left off when it comes to looking at trig functions and these using these fundamental identities, which you see over here on the right. The fundamental identities for the reciprocal identities, quotient, and Pythagorean identities all are essential to using these as kind of building blocks or pieces that we use to disintegrate these complicated trig functions. So what you see here is something that you've done before, this pink simplify instruction, and then on the right you have the prove the trig identity. Now the pink simplify the trig expression, if we look a little bit closer, is what we've been doing before. We were using a trig identity, secant squared theta minus 1, and turning that into tangent squared theta minus 1. And we worked through trig or algebra like we mentioned before the break. And we come up with a sine squared over cosine squared over 1 over cosine squared. And we use a little bit of algebra to get this to simplify to be sine squared theta. And I'm using all of what I know from the fundamental identities that we had before in our notes. So that process was a little bit strange because you were just sort of expected to know that, oh yeah, sine squared theta is the least complicated I can get it. Whereas if we look at verifying or proving the trig identity, you actually have an end goal, which is given to you on the right side, which is why you're proving the identity. We know these are equal, but we want to show that this left side looks like sine squared theta. So we're using the same strategies. We use trig, we use algebra, and a little bit more algebra, and we simplify and verify, and I put a check with this redundant statement saying that, oh yes indeed, this cosine squared and that cosine squared divide away, and I'm just left with sine squared theta. So this skill is a little bit more well-defined than just simplifying an expression. So if we look at our first example, let me get this out of here real quick. If you look at our first example, the verify example has tan squared x plus 1 times cosine squared x minus 1, two binomials multiplied together, and they equal negative tangent squared x. For tangent squared x plus 1, and that looks like a Pythagorean identity because I see a squared in it. So if I don't remember it, there's no shame in us going back to look at it right now. That looks like this middle one here, 1 plus tangent squared x equals secant squared x. I'm saying x instead of theta. It's just a variable. So, okay, yeah, I know that that can simplify to secant squared x if I just shuffle those things around. And same thing for cosine squared x minus 1. I know that 1 equals sine squared plus cosine squared x, and I can subtract 1 to this side, so I get cosine squared x minus 1, and that'll equal negative sine squared x. So I can shift the identity that I already know around so I can use it and substitute for it. So because these two things are equal, I can substitute one for the other. And that helps me out a lot because I want this whole left term, which is multiplication of two binomials, to become one single term, negative tangent squared x. This is why these are a little bit easier or a little bit more well-defined because we know what they ought to look like at the very end. Here, this is going to help me out greatly because instead of, well, if I multiply two binomials together, which would, like if I took an algebra step at the very beginning, that would look really complicated. So it's important I didn't do that. It's important I used a trig step. And I can continue with this trig step by writing secant squared x into 1 over cosine squared x. And then I can carry on with an algebra step, and from there, that division should get what I need, so this negative tangent squared x. So thankfully, we have an end goal given to us already. Awesome. All right, now for our second example, I wanted to start this one off fresh with you all. So the question that we'll struggle with early on is, which side do I start with? And that really comes down to what you're comfortable with. Do you want to turn the left side into a single term, or do you want to turn the right side into two separate terms? Personally, I like the idea of making like two different terms look like one term. So I'm going to try that. So I'm going to do what I know I can do in the first place. I've got those two terms. If I just use my quotient rules, my reciprocal rules. And it looks like I'm a little stuck because I used my trig ideas. And I want to use something from algebra now. And I should be thinking, well, if I have two fractions and I want them to become one fraction, then I need to have a common denominator. So I know that my common denominator has to be sine. So, well, over here on my left, I already have a sine as my denominator. But on my right, I don't. I have to multiply in a sine. So if I multiplied in a sine, which I'll show that up here, and of course I'm allowed to do this on one side of my equation without touching the other side of the equation because I'm multiplying by 1, then that will help me add or subtract these fractions together. And it looks like this fraction will become one term if I'm able to remember the trig identity that goes with this appropriate 1 minus sine squared. And I do remember because it's a Pythagorean identity. That's cosine squared x over sine x. So again, this 1 minus sine squared x becomes cosine squared x. Now, this is where you want to make sure you're referencing the goal you have. Okay, I want this to become cosine cotangent. Well, it looks like I have a cosine already in my numerator, so I'll set that thing to the side. And then I have a cosine x over sine x. Oh, okay, yeah, I remember that's cotangent, of course. So, we got it. We got what we need. And it's kind of nice because you have an end goal, and you can check those things. But some important things to remember here is, are you more comfortable maybe starting with two separate terms and making them look like one thing? Or are you more comfortable breaking this one term apart into two separate functions? Which you can kind of see how it would appear. It would basically be reversing this process and going from, oh yeah, I know cosine x times cosine x over sine is cosine squared over sine x, and then you basically go backwards from where we started. So if you want to try that, you're welcome to. Our third example is going to look at this two-term secant x plus tangent x equals cosine x over 1 minus sine x. Something important to remember here is to think about, well, what do you want to do first? Do you want to work on the left or work on the right? And I chose to do both of those things, so I'll just show this to you. I knew that if I worked with the left alone, I would have to turn it into sine or cosine, and I would have to also make sure that the denominators were the same, which they were in the first place. But then a really tricky step in this process was using a conjugate, and this is a skill that, this is actually an algebra skill, is multiplying by the conjugate. Oops, conjugate. And if we don't do this, then we can't force a difference of squares situation. And that's important because a difference of squares, when it comes to trig functions, looks like a trig identity we know. And then we can simplify from there. So I take my cosine squared, which is what 1 minus sine squared x becomes, making sure I've distributed everything correct in the denominator. And I can now divide out the cosine that I've factored. I really didn't need to distribute it, that I factored from the denominator. And then I get the right side that I started with. Now, if you didn't like that way, you're welcome to start off with the right side, but it still requires multiplying by the conjugate here in this step. So be wary that that's an algebra skill that can pop up here. Factoring, like in this step, factoring out a cosine from the first term and a cosine from the second term is important to reference as well. So I wanted to give that to you. We're approaching 13 minutes here, but this is the homework that I wanted to, it's not really homework, but it's practice that I wanted to share with you. I'd like you to try these. If you can get these down, let me get it full. There we go. If you can get these, then you have a pretty good grasp of what's going on with verifying trig identities. Use your Pythagorean, your reciprocal, and your quotient, and a lot of the algebra skills that I passed on to you. So let me know if you have any questions, and I'll talk to you guys later.